Okay, hello everyone. Welcome to the 2024 Wolfram Technology Conference. This is our 36th annual technology conference. And yes, it is a long-term business to make the world computable. It's kind of been the same vision all of that time, all of these years, the 38 years since we started our company and so on, and probably 45 years altogether since I started working on these kinds of uh, directions. Actually, I was just pulling out things that I did in 1993 recently because I just finished the project that I started in 1993, and it was very satisfying to find out that the old Mathematica Wolfram language notebooks that I had back in 1993 just ran without change today. That's an encouraging thing. We've been building this sort of big tower of capabilities, and what we've noticed over the years as we build to one level, we get to build yet another, yet more, and we get, in particular, to see from what we have built, we get to see what's now possible. And that's been sort of an exciting process, and it's been something that's really been building over the years. It's also very nice to see that in recent times, these are kind of our years. The things we invented decades ago are finally kind of coming to fruition. Though I think it's fair to say that much of what we have is still, for many people, an artifact from the future. And it's always particularly fun to share artifacts from the future. And I know many of you here have been using for many years our artifacts from the future and getting the benefit of doing that. Well, we're now sort of having the opportunity to deliver kind of our computational superpowers, not just to humans, but also to AIs as well. They're good customers too. So what I'm going to do here, I'm going to talk first about some new technology we have. I'm going to talk about things we're doing in general. I don't think today I have an awful lot to talk about here. We're not going to have a chance to do Q&A today. We'll have a chance to do that tomorrow. So I will also say that almost everything that I say will be covered in more detail at some other talk at this conference. So I encourage you to check out all of those. All right. Well, let's dive in and talk about Wolfram language and Mathematica features. So at this conference last year, we were heading for version 14.0, which was released in January. And now we have, start sharing here. In July of this year, we released, that was version 14. In July of this year, we released version 14.1. Should make this a little bigger, shouldn't I? And right now, we're just closing off version 14.2, which should be available soon. And plus, there are a lot of things we're working on which are not really aligned to the Wolfram language calendar. All right. Well, let me show you some things. So, as I said, we're in kind of a long-term business, and the let me show you something, first of all, that we first thought about around 1990, and we finally figured it out. We finally have the technology, the ideas, and so on to make this work. It's a fairly technical thing, symbolic arrays. So this is something that sort of first arrived in version 14.1 and is being enhanced in version 14.2. So let's say I want A to be a matrix. Well, it's supposed to be an n by n matrix. I don't want to say what its elements are. I don't even want to say what n is, the size of the matrix. I just want to treat the whole thing symbolically. Well, now we have a mechanism to do that. I think maybe I'll make this even bigger for right now. And so a matrix symbol has a name, just like any other kind of, just like an ordinary symbol. It has a way to specify its dimensions. So we can use it here. So, for example, we can say what are the dimensions of A, and we'll get that it's n by n. We could say kind of symbolically, what's the inverse of A? We get that. We say, what are the dimensions of that inverse? It's still n by n. Okay, we can say, let's have a vector symbol v. What are the dimensions of A dot v? Okay, it knows that that's just n. We can compute v dot A dot v. That just shows up symbolically there. Now, if we wanted to, this is a new thing in version 14.2, we could do a component expansion of that. We could see that explicitly as indexed components. We could also start doing some calculus on matrices and vectors. So we take the gradient of that and we get that result there. And we could, for example, we could look at just this vector v, and we could say, what's the derivative of v with respect to v? Okay, that's a funky new object. It's a symbolic identity array, which is an n by n identity, symbolic identity object. So we could say with n equals 2, what actually is I2? And the answer is it's the identity matrix, 2 by 2 identity matrix. We could also tell it that we want a vector v that has a bunch of real numbers in it. Now we can say, what's the derivative of v with respect to that v with respect to itself? And we get this result here. Or we could, for example, let's say, what's the third derivative of that vector? And now it becomes a bit more complicated, and notice that we're using that symbolic identity object and so on. But we get to kind of do everything symbolically here. So let's say we have a 3 by 3 by 3 tensor. We'll see that little 3 up there. And we can now say, what's the derivative of the total of that tensor? So it's a kind of a trace with respect to the tensor. And we get this strange object now. We can look at what it is. This is a symbolic delta product array. It's kind of construct. It's sort of a tensor constant, so to speak, that we can construct there. These are the kinds of things we need in order to represent, do purely symbolic operations on things like tensors, and kind of the some slight kind of conceptual complexity of this kind of is sort of, I think, the reason that it's taken us a solid 30 years to actually develop all of this. Well, in version 14.2, we have things like array expand. We can expand matrix powers, things like this. We can say, what's A inverse, B inverse, C inverse? Okay, there it is. We can say array simplify that. We get that result. Well, let's, for example, one of the things that's really nice, and in general, we want to make our language be able to be sort of a notation for things. And here's something where you can do kind of a pure textbook kind of thing. We take the norm of A dot x minus b squared. We get that in traditional form. It looks like just like it would in a textbook. But now we can actually take that object, differentiate it with respect to x. We actually get that result. We can go ahead and take the second derivative. We get that result. We could go and take the third derivative if we want to. That's a slightly more complicated object. But the main point is that we can take things that are in very much sort of textbook type mathy notation, and we can actually now explicitly compute with them. Okay, so let's see what else we could do. Something else here. We could say we could do something like this, a line integral, in which we say that we're integrating with respect to this vector, which is that particular line, x dot x. We compute that that result. So that's kind of one new thing in version 14.1, 14.2 is symbolic arrays. It's been long requested. We've long thought about it. Finally, now we have it. Let's move to another thing, from symbolic arrays to concrete tabular data. Another thing that we've long been interested in. How do we deal with gigabytes or even terabytes of data directly in Wolfram language? And that's something that we're now in a position to do, thanks to a new construct that's being introduced in version 14.2 called tabular, or dealing with tabular data. So let's take a look at that. So let's say we just take some very small data set. and we load it in, and we say, make that a tabular object. So there it is as a tabular object, and you can kind of scroll through the data set if you want to. There you see it. Now, tabular is for kind of dealing with large two-dimensional tables, many rows, many columns, many labeled columns. Underneath, we can think of it as lists of associations, but it's packaged together in this tabular object that's highly efficient and where there are lots of operations that are supported on it. Our dataset function allows arbitrary hierarchical data, and gradually tabular will move closer to dataset and vice versa. But tabular is really about sort of the simpler case of truly two-dimensional data where you can do a lot more. It's kind of like compare what you can do with polynomials to what you can do with general mathematical expressions. Tabular is kind of like the polynomials in that analogy, and it's something where you can do a lot more operations on this purely sort of two-dimensional data. So you might get the data by reading in a tabular from a CSV file, or there's typically new import elements, tabular import elements, read it in from Parquet or Arrow or whatever. You can pull it in from data stores, and it deals with all the authentication stuff, the S3 or Dropbox or whatever else. Or you can use an external database and in fact do operations right on the external database, kind of compiling them from Wolfram language automatically. So the kind of the way you start is you can use toTabular, which will take sort of something with lots of kinds of structures and turn it into a tabular object. And in fact, as we've developed tabular, we've found that there are lots of constructs that we've needed that we can also make work on lists and data sets and so on as well, and made those much richer. So kind of let me start showing you some things with tabular. So this is, we're sort of introducing a bunch. Okay, so let's take this tabular for this Titanic data set. And there's a new function, transform columns. We take the date of birth column, which, oh no, we're going to transform columns. So we're going to create a date of birth column, and we're going to take the age column, and we're going to take 1912 minus the age. And so now this will create a date of birth column for that tabular data set. And now we can go and say something like, we could instead say, kind of construct a data set. So transform columns will take an existing data set and add columns to it. Construct columns will construct a data set with just the columns you specify. And for example, we could take that, and now we could take that tabular, and we can do this. We can say, I want to take that tabular percent and make a date histogram of that particular column in the tabular. So that's kind of a new mechanism for extracting data from tabulars, and you'll see it'll work on a lot of other things as well, to be used directly in visualization functions. Okay, so here's another thing you can do. Let's aggregate rows. So we're going to say we're going to take, we're going to aggregate rows by class. So, and we're going to create a column here that is a count of the of how many people survived in that of the number of elements, number of rows that had survived for survival status. And there we were able to create that tabular by aggregating rows in the original tabular. All right, so I said this worked on larger data. Let's get a larger data set. This is a data set of all the trees recorded in New York City. And let's see, we can just ask what are the, and so lots of functions just work directly on tabulars. So here we can find out there are 683,000 recorded trees in New York City. And let's find out what's known about those trees. So we'll say, what are the column keys for the trees? And these are their native names. So we didn't make these names up. They could be curated. We could map these names into something more Wolfram-like. But that shows us the raw data. Now we can say, for example, let's aggregate rows. Remember, just like I aggregated rows in the Titanic data set, I can aggregate rows by borough for a count of the number of trees. So this is going to give me the number of trees by borough in New York City. Okay, I could also say, let's count the number of trees here and also give a sort of the most common tree from of the species that show up there. So now it'll have to do that computation. So it tells us the whatever these trees are, these are the most common trees to be found in those different boroughs. Okay, so let's go ahead. Let's see what we're going to do next. I just did this one. Oh, no, there we go. No, I'm going to aggregate rows, but instead of doing, instead of aggregating by borough, I'm going to aggregate by Latin name. And so this is going to give me for each, this is going to aggregate all the different types of trees by their Latin names. It's going to give the common name, I guess, and it's going to give a count of the number of that kind of tree. So for example, here I could go ahead and I could use sort by, and now I could sort by. This is again a new syntax for sort by. This is using just specifying the column information here. And I could say sort by column, and this is sorting from the least common tree to the most common tree. Okay, so let's go ahead and take that least common tree. Let's select from New York trees ones where their Latin name is Pinus virginiana. And now we'll do that. There are 10 of those kind of pine trees. And now we can, for example, one of the columns here, there are lots of columns that we'll see here, but two of the columns are latitude and longitude. So we can extract for all the pine trees, we can extract latitude and longitude. We can then use the function from tabular and tell it we just want those as a matrix. So those are the lat long coordinates as a matrix. Now we can go ahead and say, I want to make a geolist plot of these various rather lone pines, it seems, scattered around the New York City area. Well, now to just sort of link this in with other kinds of capabilities, we might say, let's go ahead and take all those pines and let's do a geolist plot where we get the geoposition of the pines, 50-foot radius around the pines with a satellite image. And so we can see here, well, the point didn't quite, whoever measured this pine, they didn't, I think there's the tree and there's the point, not too far away. And we can check that's where all the trees is very, very urban area, I guess, and a few trees there. So that's some of what we can do with that. So let's go back to our New York trees tabular again, and then let's do some other things with it. So for example, one thing we can do is make a pivot table. So we can say, I want to look at this with respect to the number of trees with the Latin name and the health of the trees. So what we'll see here is now we've sort of pivoted around. So we've taken the values of the health parameter, fair, good, poor, and we've used those as columns here. And now we've arranged those by, we've grouped those by the Latin name for the tree. And this is now that result. Okay, well, one of the things that happens in real world data is that things are missing. So for example, we might have a piece of a tabular data set, and there might be some elements here that are just missing. Well, one of the things that we have in dealing with tabular is a bunch of powerful functions for dealing with missing data. So for example, one way you can transform away the missing data is just replace every missing data point with the mean of that particular column. Or for example, we could go ahead and we could do something else. We could say use interpolation. We can also use all sorts of machine learning techniques for this. But let's go ahead and this is now going to just select New York trees with we're selecting ones that in this particular case, the stump diameter of the tree wasn't explicitly said to be missing. It was just set to be 0. So here we selected ones where it wasn't 0. And now we can go ahead and take those and use the same mechanism that I did before, make a histogram from these by just saying use the stump diameter column to make the histogram. Now we can go ahead and take that. We could go and let's go back to the Titanic data set, talking machine learning. And let's go ahead and use machine learning to just learn the distribution of rows in the Titanic data set. And now we can go ahead and just generate synthetic data, basically, from the Titanic data set. So this is fake synthetic data. Age minus 0.3 is a bit unconvincing there, but so it goes. That's what happens with machine learning. Now we can use the same mechanism we did before to make an aged histogram for the synthetic data we just produced. We could also, for example, we could compare that with the actual age histogram that we made before. All right, so what I've been showing you so far is tabulars that are all in memory, running inside Wolfram language. And it's been set up so that that's extremely efficient. And we can certainly deal with many gigabyte-sized data sets directly in Wolfram language on a typical computer. If you want to go even bigger than that, or you're just dealing with remote data, you can also just connect to a relational database. And so here, for example, we connected to this relational database. It had a particular schema, and we could say, make me a tabular, which is just the customer's table of this in this particular schema. Now, if I wanted to, this is a remotely represented object, and we've got all kinds of information about what it is. But if we wanted to, we can say to memory, and this will pull it in to memory. And that will now, it took a moment there, and it pulled it in from that external database and put it right in local memory. You can do operations, many of the operations I was showing you before, all of those operations can be done with the exact same syntax in Wolfram language, but if you're doing them on a remote tabular, they will be actually executed as operations in the relational database. And sort of transparently, as if they were being done directly in Wolfram language. If you pulled the database into memory, or a piece of it into memory, then you could do them the exact same operations locally. Okay, so as I say, there are many operations that we kind of developed in working on tabular, which are useful elsewhere. One very simple one is just the function discard, which is the analog of select, but it discards things rather than selecting things. That turns out to be a useful operation in dealing with tabulars. All right. Well, so I talked about tabular data a bit. Sort of a theme over the last several years is handling sort of big data everywhere. And in the last several versions, one of the things that we've been working on is handling videos. And so I can load in a video. Here's some simple video. What is it doing? It seems to be a video of somebody walking a dog. Okay, we can now apply machine learning to these kinds of things. So for example, here a new function coming in version 14.2 is video object track. Let's see what it can do here. Let's see whether it manages to go through that video. It'll have to process the video and grind. Let's hope it manages to do this. It may have to load in some machine learning, some networks and so on. So just do it. Still processing. Come on, wake up. So what's interesting about this is going to generate some things that represent the tracks of objects in that video, and it's kind of symbolically representing the tracks of objects. Sort of a similar problem to representing something like the track of a plane going across the country, which we've had to deal with. All right, it doesn't. For some reason, it's not doing this. I should explain that I'm running this morning's latest prototype version 14.2 builds. So that means that all sorts of things can go wrong. This is always a good way to test new systems, but I kind of wanted to show you the very latest thing that we have sort of cooking here. All right, here's another function. Let's see if that works. Okay, this is a video summary plot, kind of a convenient visual way to get a sense of what's in a video. And one of the things we've been doing in handling videos is to set it up so that all sorts of operations can be done uh, directly from videos. So here's a video of a little chirping bird, and now I asked for the spectrogram, and we got back the spectrogram of chirping bird. We could probably audio identify that. It'll say it's a bird chirping and so on. Another thing that we've done is kind of functional programming meets, programming meets videos. So there's a new construct here, which is sow video and reap video. So what this is doing is it says video map list. That's kind of a piece of sort of video programming. If image contains Q, if the image contains a bird, then sow that image and reap the resulting images. So what this is going to do is it's going to go through this video, hopefully, and it's going to process the video, and it's going to, for every frame, it's going to figure out, is there a bird there or not? If there is a bird, it's going to sow that frame, and then reap video is going to collect those frames, and hopefully what we'll get is a video which is just a video. Why isn't this playing? Video play. There we go. Okay, so this will jump around probably because it's only going to show the frames that happen to have a bird in them. Okay, so another thing we could do is this is a kind of functional programming with video. There's a video frame fold where we're removing background and composing video. And again, we'll be assembling the video frames and getting the results. I think we have a lot of time left to go. Well, maybe I shouldn't bother with this. No, that was the video as far as we got it. Okay. Well, other things we can do. How about audio? One of the things that's we've been doing. Let's capture some audio. Hello. Try to capture audio. It would look better if I had the right microphone connected. Yeah. I wonder what I should use here. Fascinating. I am going to guess it might be that. Hello, hello, hello. Hello, hello, hello. Well, let's see. Zoom audio device, maybe. Hello, hello, hello. Hello, hello, hello. No, I don't seem to be able to capture audio. Oh, well. What I was going to show you was some new speech recognition capabilities, really basically real-time speech recognition together with all kinds of annotation of the speech, like breaking it into sentences and so on, and being able to get speech fragments from those different sentences. And in general, we're kind of taking the things that we've done with in machine learning, and they're all getting more efficient as a result of better machine learning hardware. So, for example, on an Apple device, will be by default using Core ML for pre-built machine learning stuff like image cases and so on. And we have the ability to have target device arrow GPU when you have a GPU. We also, by the way, have a lot of things for when you custom build a neural net in Wolfram language. There's a lot of new capabilities there. Let me show you something. Well, here's a oh yeah, here. This is using there's just a faster image identify. But we can also actually, if we look at the image identify network, here we go. Here's the net model that corresponds to image identify. We can open this up. One thing that's new is that we now have much more beautiful kind of publication quality output illustrating neural nets. And so if you build your own neural net, you can just sort of extract this using the information property of net model and put it in the things that you're writing and so on. So one of the things we're doing is trying to make sure that our machine learning capabilities are based on sort of the most efficient underlying hardware and software stacks. We've introduced net external object, which is a way of pulling in external models that are represented in, for example, ONNX. And we're building a link to PyTorch. That's a much messier story, but we'll be able to take any model that exists in that format and run it directly in Wolfram language, in addition to one being able to symbolically build one's own networks in Wolfram language and being able to kind of mix and match networks that are represented externally with networks that are represented in Wolfram language. Well, okay, another area that, again, is a sort of high performance area is PDEs, partial differential equations. It's been a multi-decade story building up a kind of a tower of capabilities in linear algebra, now assisted by GPUs and so on, in geometry, computational geometry, etc. We've been investigating for years using neural nets for these kinds of things. Maybe we'll end up doing that increasingly going forward, but right now we're just using the most efficient kind of finite element methods and so on. So one of the things we've been trying to do is steadily expand the kind of library of representations of the physical world that can be used with PDEs. So representing things like heat transfer, mass transport, acoustics, solid mechanics, fluid mechanics, electromagnetics, one-particle quantum mechanics, and so on. So let me show you something from electromagnetics. So here's a piece of geometry. We can look at that piece of geometry. There it is. Now we can say we're going to use that. That might be a conductor. We can define some variables here. We can define some parameters. Let's say the thing is made of copper. Let's now define, and this is where we get sort of our modeling language, our symbolic modeling language. We're defining a PDE that has an electric current PDE component, electric potential condition, that's a boundary condition, and so on. And now we can take those equations, those variables, that region, and we can just go ahead and solve the differential equation in that region. We could take the function that we get out from that differential equation, we could find its gradient. So we're finding from the electric potential to the electric field. And now we could actually just plot the electric field and in that over the region that we've defined there. Let's see what happens. Wake up. Should work. Okay. It's so easy to solve the PDE, yet so hard to plot the result. Oh, there we go. All right, nice looking plot. That kind of shows the electric field, the magnitude of the electric field as along this conductor. Well, something we're adding in 14.2 is magnetostatics. So for example, here we're solving a solving for the magnetic field of a region that looks like that. And let's see what we can do. Let's try and make a plot of that. We're going to plot the magnetic field here in that region around this object. And we could have done that in 3D and all those kinds of good things. Well, again, on the subject of differential equations, we've added a bunch of capabilities for ordinary differential equations. So this is working out the fixed points of differential equations. We can kind of make a stream plot showing where those fixed points are. We can work out stability conditions, or symbolically for this, we could, for example, figure out the region of stability for this particular differential equation as a function of those two parameters, A and B. Okay, another new thing coming in version 14.2 is game theory. So this is something people have been asking about, and sort of the challenge has been to come up with a good design for that within a good kind of symbolic representation for games. This is a matrix game. We can look at kind of the data set representation. I think these colors are going to change before we finally release this. This is just a prisoner's dilemma game. Now we can make kind of a matrix game plot. Again, this probably changed before we release it. Sort of a visual representation of this game. We could take a more complicated game. Here's a slightly more complicated game. And we could now say things like find matrix game strategies for this particular game. Strategies aren't terribly exciting there, but it found those strategies from the optimal strategies for this particular game. We could also represent a tree game. Here we have a tree game, and we could make a plot of that tree game, and there's the result. There's just adding another area to the things that we can represent symbolically that will sort of connect with everything we do in linear algebra, linear programming, et cetera, et cetera, et cetera. Okay, well, maybe thematic for the game theory. Another thing we added, we've been progressively adding more and more data on lots of kinds of things, more and more computable data, whether it's about nutrition, where we now have pretty much the world's best collection of nutrition and food data, or whether it's about historical countries. So here we could say, make a plot of the Roman Empire in the year 100 AD. Maybe we could look at, let's compute the geo area of the Roman Empire as a function of time from 0 to 200 AD, and we see all kinds of things that happened over those years. Well, it's actually pretty complicated to think about historical countries independent of defining what it means to be a country and so on. We kind of are thinking about these complicated regions in space-time that represent particular countries that can merge and split and so on. So we can ask questions like geo-identify, what historical country is London associated with? So we'll see a sequence of different countries that London was included in. So for example, we could say something like, this will show the dates for all of those. So that's showing the date intervals for each of these. And we could, for example, say, what's the one that had the longest duration? So what's the, what country was London in for the longest? Okay, Kingdom of England from 927 to 1707. We could also do something like say, what were the geo-entities associated with the United Kingdom 800 AD? And here they are. And now we can say, make a geo-list plot of those, and we'll get a map of the configuration of the country at that time. Well, many subtle things to do with, it's just sort of an example of how complicated it is to make the world computable. So for example, we could say, what's the distance, 100 AD, what's the shortest distance between any place in the Roman Empire and any place in the Han Dynasty? But that is different from this geodistance. That geodistance is asking something. If we think about these historical countries in space-time, this is asking if we look at the if we look throughout space-time, so to speak, when did the region representing the Roman Empire ever get closest to the region representing the Han Dynasty? And we see it got a bit closer. Well, let's see, what are we doing there? Oh, we can just look at what that looks like. There are all kinds of issues. For example, this is the Union area is the largest area ever occupied by that historical country at any time. So we project that space-time region down into kind of a space-like surface that sort of projects any place it's ever been during that period of time. Let's see. Yeah, we can do all kinds of things. We can make this time series of polygons for the Roman Empire, and just yeah, we can compute all kinds of things here. What are we doing here? We can try and we know about all sorts of different features of history. Again, we're sort of trying to make everything computable. Those are battles in France between 200 BC, 200 AD. We could also take what we had done. Yeah, here we go. We can now make a time series. We take geographics of the Roman Empire. And what we're doing is we're making a time series. This is going to be a slideshow video looking at the time series. So we just created a video of the growth and decay and so on of the Roman Empire over that period of time. And that was making use of both our computable data and our ability to make videos and so on. So a nice collection of different capabilities put together. All right, let's turn to a different area. Let's talk about chemistry. We've had a very serious effort in chemistry over the course of many years now, and chemistry is an area that's very suitable for symbolic representation and computation. And I think we've gone a long way in building kind of simply the best computational chemistry system ever, and we'll go even further. It's relevant both for professional chemists and for students using our technology directly or through Wolfram Alpha. Let me show you a few things here. Let's find isomers of heptane. So this will now go through, and there are a few isomers of heptane molecules. We could say, for example, make a molecule plot 3D of all of those. So there will be our three-dimensional versions of those molecules. Now, something that's new in 14.2 is a molecule mesh. So we can kind of go from molecules to computational geometry. So what this is doing, and there are various different ways to do this, this is making a kind of a mesh that represents the 3D geometry of these molecules. And so, for example, we can just compute the surface area directly from one of those meshes. And we could, for instance, go ahead and compute, let's say, for each of those molecules, we could compute the volume of the molecule mesh and the surface area. We could plot those, and we could label them with the molecule plots. And so now we'll get a picture of the isomers of heptane showing the volume against surface area for those isomers. So we can see their different shapes and so on. So that's chemistry, organic chemistry. We also have done a lot with biomolecules. And so, for example, here, let's pull in a biomolecule that is a protein. And what can we do with that protein? Well, we can say make a biomolecule plot 3D of that protein. There's our ribbon plot of that particular protein. If we wanted to, we could take both the take both the ribbon plot and the direct plot of the molecule with all of its atoms and so on, and we can see how those correspond. We can take, using our external identifier mechanism, we can get biomolecules from things like Protein Data Bank. There's a molecule from there. We could also go sort of ab initio. We could just say there's a peptide with a particular, that's a particular biosequence, and we can do things with that. Actually, here, let me do something more gutsy. We'll see whether it works. Let me just randomly join 30 base pairs, and now let's make a biosequence out of randomly joining, let's say in this case 45 base pairs. Now let's see if we can translate that to a peptide, there it is. Now, it may be a reasonable peptide, or we may have got stop codons in the middle of that, but we'll find out in a moment. Let's say make a biomolecule plot 3D out of that. Okay, well, it wasn't very exciting. It's just an alpha helix there. But what this did was it used an LLM to go and try and do the protein folding and figure out a structure for this particular protein that we specified by this random sequence that we got from these random base pairs. And right now, well, we're moving towards using a local LLM for all of this. We could actually take that object, and because it's all represented symbolically, we could take that and we can just make an explicit molecule plot, I hope, of this, if it manages to compute the coordinates of all the atoms. I wonder what it's doing here. It's taking lots of time to do that. Well, I'm not sure. That's what I get for picking a random peptide, and not even longer than the immune system picks in an antibody. Okay, well, I don't know why it's taking so long to do this. I was impressed that it managed to do the protein folding so quickly, but now it's doing this rather slowly. Well, in any case, the let's move on to another area. So another area we've been building out in recent times is astronomy. Again, we've been trying to build kind of the world's best ever computational system for astronomy. Again, a place where the symbolic representation of things is very important. And we are steadily kind of adding capabilities for astronomy. So, for example, that was we could all of the kind of capabilities that we have in the rest of the system, like projections, for example, we can immediately apply those in computational astronomy, and even things like the ability that we added a few versions ago to have axes of any shape is really important when you're trying to draw an axis that corresponds to the plane of the ecliptic or something on a projection of the sky. Well, we've got lots of kinds of computations, astronomical computations. Here's the distance to Mars computed for the current time. We could, for example, plot the distance between Mars and Earth over the next over a decade, and we see that yes, there are certain launch windows if you want to send lots of stuff to Mars. Now we could, for example, we could ask new capability coming in version 14.2, find an astro event. So this is now finding the perigee, the closest approach to Earth of Mars. The next one is January 12th of 2025. We could also ask a question like, when will the Earth rise over, if you're on Mars and you're on Olympus Mons on Mars, when will the Earth next rise from that location on Mars? So there's the result. And all sorts of things we can compute. We can compute the absolute minimum separation on the sky between Mars and Jupiter in the period 20 years happened in 2020. And we can look at what was the actual separation. It was 0.1 degrees. That's very close. So all sorts of things. Here's a thing I happened to just do in a request in a demo I gave a couple of weeks ago. I thought it was really cool, so I'm going to show it to you. This is just using astronomical data that we have. This is data on all the known pulsars. And if you take all the known pulsars, and this is showing them in a heliocentric coordinate system, XYZ coordinates based on the solar system with the origin at the sun. And if we just make a 3D graphic of that, here we see the location of the pulsars. And I thought it was pretty cool because you can see the plane of the galaxy. You can see this kind of halo around the galaxy. You can see the Magellanic Clouds orbiting our galaxy and so on, just from the positions of these pulsars, all from data that's part of Wolfram language. Well, as I say, we're accumulating data on lots of kinds of things. Something that we added in version 14.1 was a lot of capabilities, a lot of sort of a new structure for representing hierarchical entities. And so this is asking for the predators, the things that get eaten by cheetahs. And so, for example, we could make an image collage of that. There's the result of critters that we've recorded are eaten by cheetahs. So, or we could do something else. Here we're looking at birds, and we're plotting the weight of birds against the lifespan of birds. By the way, you see the nice feature here that a lot of this data has error bars, and you see the error bars plotted in this plot here. Okay, well, from in Wolfram language and in Wolfram Alpha, we're maintaining lots of domains of data, from information about flights to earthquakes to music acts and so on. One of the things that you can do now is go to there is a raft now, we call them, and you can go to this eye underneath the raft, and you can pull up information about that. So if you see an object, you can pull up information, the documentation about that kind of thing. So this is a species phyletic group, and you can find out about those from this by just using the raft here and on any entity and clicking the I button. Okay, well, we're always trying to kind of tweak and improve kind of the structure of the language to make things more and more convenient. Here's something that we added actually in version 14, CoMap. So map would take a single function and map it over lots of elements. This takes multiple functions and maps them all over a single element. So you're kind of wanting to show several different attributes of a particular thing, use CoMap. In version 14.2, I guess we're adding association CoMap that conveniently sort of labels those things in an association. Other kinds of language tweaks, we're adding nearest has long had the ability to reference different kinds of things that you want to get out of the nearest. So here, for example, we're saying that we want this select to select by the index of the object and select, no, to give us the index of the object that we have selected with oddq here. Well, lots and lots of tweaks. This is just one that I liked because it was useful to me with Boolean functions. All right, this is another language feature. So we now have just a simple top-level language representation of essentially control equals. So control equals gives you natural language input, but now you can just straight type the natural language input with equals bracket like this. And there's a function underneath that. It's called freeform evaluate. You can use freeform evaluate to just take a string and compute the interpretation of it, and you can do kind of funky things. What's this doing? This is trying to take freeform evaluate of every X followed by every letter of the alphabet. This may do crazy things. It's probably taking it a while to figure out what all of those are. Okay, here we go. So some of them, let's see, XF didn't turn into anything, but wow. Some of these, that's probably Roman numerals, all kinds of weird things that you find sort of in the semantic space of what X something might mean, Greek letter psi, and so on. All right. So let's see. The something that we've been doing quite a lot of is adding sort of typing affordances. So setting it up so that that's a good example of this. So that I'm going to have a hard time finding an example here. We've made it so that lots of things about the detailed coloring of things as you type, the way that brackets autocomplete as you type, those kinds of things. Something that is new, and I'm looking for just one example. Here we go. Here's going to be an example. Oh, it is an example, but you can barely see it. I pressed, okay, I'm gonna give you an example here, which let's say we have alphabet again. Y here. Okay, if I click on alphabet, you'll see that both instances of alphabet light up. And this is something that is scope aware. And it's just one of these conveniences in being able to type more efficiently and understand what you've typed better. So other things, just things that sort of flash and autocomplete in just the right way. I have to say, as an old dog, I was pleased to have learned a new trick recently. I've always been typing functions that with ampersands, and you have to use parens in a case like this just because you can't, otherwise there's no precedence for function that will work in all cases without parens. And I just learned the trick of you can type the word function here, which of course I put in, that was a feature of the language that I put in 35 years ago, but I hadn't used it, hadn't really internalized that it was useful, just as a way to avoid typing parens and the ampersand. But it's good to know that at least this dog can still learn a few new tricks. You know, we've been steadily progressing in putting in all sorts of autocomplete capabilities. So for example, here, if I go to the assumptions, you'll see that this autocomplete, I'll bring it up again, that autocomplete now has, I can kind of tab through, that has this field here. So the autocomplete has an actual field that you fill things into. And that's kind of a new feature of autocompletes, and you'll see more and more being done with autocompletes, which have been a very successful way to help one sort of type better. Okay, well, going from human, oh yeah, I should mention something else as well, which is one of the things we've done is to add kind of fuzzy autocompletion. So if I just type RF, resource function is one of the autocompletes. That's very convenient. It makes one it's just a typing affordance. So another thing that we've added is the notion of elegant code formatting. So Wolfram language I view as being kind of a notation for computation. And one of the things that's important is that you can make it when you write it in have it in a document you're writing or something like this, you can have it really look as elegant as possible. So we've added this screen environment called elegant code that one's encouraged to use if one's writing things where one is putting Wolfram language code as part of the exposition of what one's doing, and certainly something I do in the things that I write. And it just, if we find a more complicated example here, we'll just find that an elegant code is just easier to read as something kind of a thing that you read. It's not necessarily, it's okay to enter as for sort of everyday programming, but what's really important about it is that it kind of has its appearance is more suitable for expositions of things. I can keep, I'm going to switch it back actually. Okay. All right, let's dive into some other kinds of things. Let's talk about the compiler. We've been steadily progressing in building our very sophisticated compiler for Wolfram language. And you kind of get to see a little bit of the sophistication as you see things like we ask for compiler information on map. That's the actual declarations of the different data types that are used internally by the compiler when dealing with map. We could, for example, ask for compiler information about the type. Remember, in dealing with Wolfram language, usually the whole point is we automate all of this stuff about how the computer explicitly represents integers and these kinds of expressions and all that. That's all automated away. You never have to worry about it. But the compiler does have to worry about those things because it's trying to fit the things that you're doing into kind of the low-level structure of computers to make it work as efficiently as possible, to work at sort of the speed of machine code. And often it can do that completely automatically, but you can also give it hints to help it do that. So for example, here, let's see, we're looking at the integer 64 type, and that's its type hierarchy and so on. This is some of the structure that lies inside the compiler. This is some of what you can kind of hint it about when you want to sort of optimize code, and it is steadily learning to do this automatically. So here now, one of the things that's happened is the compiler, which is steadily compiling itself, by the way, and getting faster as a result, is now showing you a bit more about what it's doing. Well, let's take a look here at, let's take a look. There are some declarations of types. This is, let's see, this is now, okay, so this is something where a mistake was made. So now we can go through and we can look at the source code for what happened. Why were the types not the way we thought they should be? And we can go back and find that place where arg1 had the wrong type. And this is very convenient if you've got a big piece of code and you start compiling it, and much of it compiles, but some of it doesn't. This is part of the story of how you have to hint the system to get it to compile correctly. Okay, so another thing that's coming in version 14.2 is a new data type for the compiler, GPU array. That's an array which is being stored in GPU memory, and that's part of our efforts to make optimal use of modern GPUs. Okay, also beyond the compiler, another thing we're doing sort of a systems level is connections to external languages. So most languages like Python or something, there's a horrible zoo of dependencies and a big mess of libraries and so on. That's the kind of thing you don't have to worry about in Wolfram language. But if you want to make use of Python code, we want to make it so it's as well encapsulated as possible. So we've added a whole mechanism for uh, dealing with that. Let me type in. Let me ask for a random sentence here, and this is going to, I don't know what it's going to do, but it's this is now going to create a Python environment. It's going to install a bunch of packages, and then it's going to run the code. And as far as the Wolfram language user is concerned, it's just seamlessly working at the Wolfram language level. Underneath, all kinds of weird Python snakes are running around and so on. Another thing that related to this is the idea of external objects. So this is starting an external session, in this case also a Python session. We can say external evaluate this function. We get back an external object, which we can then poke at and do things to. And that external object is kind of owned by the external session, but we're able to interact with it directly in Wolfram language. And sort of the idea is we can now basically encapsulate anything in a transparent way. Python is done, R is almost done. C-like languages, we have a very good foreign function interface now. And so we can basically take all of these, anything that's written in these external languages and encapsulate it so that you can use kind of the symbolic representation and the power of Wolfram language and kind of its a whole documentation mechanism and ecosystem and so on. But underneath, the implementation can be done in whatever language you want. And we've been sort of steadily making lots of entries in the function repository and packlets this way. I have to say, I had thought if we have all this encapsulation mechanism that people say there are all these libraries which have been developed in the sort of world of all these different languages, it's like they're all very impressive. So I thought. And I thought we're going to get 10,000 functions from all of this by curating effectively these libraries. I have to say that effort has been surprisingly disappointing. What we find is endless bad libraries, endless bad knockoffs of things that we already have, and it's been a bit disappointing. But there's a lot that can be done, and particularly in specialized areas, whenever something has been implemented in C++ or in R and Python, whatever, you can wrap those things and make them into nice, clean function repository entries for Wolfram language and use them just directly in Wolfram language without having to think about kind of all the complicated mess of libraries and so on that exists underneath. Well, one of the things that has sort of been a big success story over the last few years is our function repository. There are now 3,000 functions in our function repository. Thank you to people here who've contributed some of those. I'd like to remind people, it's certainly something in the workflow that I use, is if you go and you say, I want to make a new function repository item here, you get the page for making a new function repository. We kind of have a lot of things that sort of help you to create function repository entries. But an important thing is that not only can you submit them to the public repository for everybody, but you can also deploy them either privately or publicly in the cloud. And a lot of projects I do, which involve teams of people, functions that get produced, we deploy them publicly in the cloud so that everybody in the team can use them, and we can immediately include that resource function in code that we're writing, and then maybe when it's cleaned up better, we submit it to the public function repository. So that kind of private repository mechanism is convenient. By the way, one thing that's also been added, again, sort of just a user interface convenience. First of all, I mentioned you just type RF to get resource function, but then you type something like, I don't know, something like this, and now you can hit the I button here, and you'll immediately go to the documentation for that function repository entry. So very much like for a system function. Well, let's see. We have other repositories as well. We have our data repository that's seeing a bunch of new entries associated with Tabular. We have our neural net repository, and that's seeing a bunch of new entries. Soon there will be local LLMs available in the neural net. Well, there already are some small ones, but much more serious local LLMs available there. We have all sorts of other repositories. This is our prompt repository for LLMs. All of these repositories are making use of the resource system underlying symbolic framework for this that allows one to build repositories. By the way, another repository, the demonstrations project that we first introduced in 2007, this has been modernized, and now this is all based on the resource system. And one thing to just remember when you have a demonstration, you can use it directly here. I hope in the cloud. This is just in a web browser, but I can also press this thing that says copy manipulate to clipboard. I can copy it. I can go, and this is something really convenient. I can paste it into Wolfram language and I have this that same manipulate right there, right in my notebook, and that's a convenient feature. And I certainly use that quite a bit because there's a lot that's available in the demonstrations project now. Okay, another important repository is the Packlet repository. Unlike the function repository, the Packlet repository is kind of an open repository, not a directly curated repository, but there are all sorts of important Packlets that are being put here. Typically, when you have just a single function, much better to just make it a function repository entry. It's much more convenient for people to just use that one function and everything else is general Wolfram language, rather than something where you have a whole sort of gaggle of functions that you have to work with. But in some cases, the gaggle of functions is exactly what you want. You're trying to build a whole environment, and there are all sorts of very significant Packlets that have been built. Here's one that seems to be particularly popular, our quantum framework, and that's something where both researchers and educators seem to be using this in large quantities. I mean, I think quantum computing is sort of a new factoring of lots of physics. I have to say, in our physics project, we kind of understand a bit more about the foundations of quantum mechanics, and actually, you'll find in the quantum framework here some things that bridge from that new understanding to the existing kind of ideas of formalism of quantum mechanics, things like quantum multi-way systems, and so on. Well, in general, we sort of see this migration path where things begin as Packlets or function repository entries and can really be used there and maybe used there for many years. And then we kind of come back through and take some of them and try and promote them to system functions that we're going to commit to for all time. And it's a lot of work to do the design necessary and the implementation necessary to get to that point. And in all those years, one can be using these things in the function repository, and some things in the function repository are always going to be more specialized kinds of things that don't belong in the main system. But it's provided us a very convenient kind of workflow for developing new functionality and delivering it as quickly as possible. There are actually a bunch of new repositories that are coming online. Let's see. For example, there's the example repository, which I don't think is we've really been talking about much yet. That has all sorts of examples. For example, here, these are examples of from quantum computation that are in the example repository. And whatever some of these are. Each one of these, this is all click to copy code. So you just take this, click it, paste it into a notebook, and you're running with it. Well, okay. So let's talk about technology in general. One thing that we've been doing is sort of streamlining the delivery of our technology. on the desktop, one of the things that has resulted in is the new Wolfram app, which is a kind of unified app that unifies Mathematica, Wolfram Desktop, and so on as a single unified app that can be enabled in different ways. And for example, the Wolfram engine, this is also being rolled into the Wolfram app so that it's a single downloaded thing that you can get. Well, in addition to what we do on the desktop, there's also the cloud. And oops, whatever. Let's see if it'll actually log me. There we go. No thanks. All right, this is the cloud, and what's happened with the cloud over the last 15 years is we've been steadily getting the cloud in just directly running in a browser to have all of the features of the desktop, and it even gets some features that the desktop finds hard to have because those are things that are directly related to the web. We've come a long way towards reaching parity. And I have to say, one thing that I always find sort of super convenient is you take a notebook and you publish it to the cloud. You just go to the notebook, you go to the file menu, you say publish to cloud, and you publish the notebook to the cloud. Oops. You publish the notebook to the cloud, you get that nice QR code, people can hold up their phones, and immediately they are looking at the notebook that you created, now published to the cloud. Why don't I? Well, I'll do this later. I'll publish this this notebook at the end. Well, the whole process of doing things in the cloud. I wonder whether this. Try this. I am dangerously here. Oh, there we go. Okay. That's okay. They've just created that that object in the cloud, and now we can. Oh, it's got some weird thing here for linking to a gamepad. Anyway, so here we go, and one of the things that's happening is the cloud has become more responsive. Of course, whenever I move that slider, we're still having to make do a back and forth with the server to update things. But one of the things that's happened is the things we're sending back and forth are getting much smaller. We have kind of native graphics being rendered in the browser on the JavaScript side, and that's something that has made things more efficient, and you'll see more of that coming in the future. So let's see. We also get to use notebooks that have been deployed to the cloud and embed them, author things perhaps on the desktop, perhaps on the cloud, then make them cloud notebooks that can be embedded. And that's, for example, how community is typically being deployed, how the Wolfram community is typically being deployed today. Well, one can use the cloud interactively. One can also set up APIs and schedule tasks in the cloud. And the cloud is the back end for a great many uses of Wolfram language. For example, in LLMs, for example, in blockchain, in addition to AIs being users of Wolfram language, blockchains, smart contracts on blockchains are also users of Wolfram language, autonomous users of Wolfram language. Particularly, we've developed technology there for creating what usually get called oracles, things where you are asking something about the real world, and you want to know it in a contract that is being run on a blockchain. We're just adding capabilities for real-time information about cryptocurrencies on blockchains relevant to smart contracts on blockchains. But that's a place where, again, it's the cloud that is powering all of those kinds of capabilities. As people may know, we also have enterprise private cloud, which is a purely private version of the cloud, which can be deployed either on-premise or in cloud providers. And one of the things that's happening in the big software engineering effort is full containerization of the cloud. and that's almost done and will be available soon, and all sorts of things like local function repositories and so on. Well, there actually are many deployment options for from the cloud to the enterprise private cloud to application server and so on. There are many deployment options for Wolfram language now, server deployment options. And the goal that we've had is that there are many different people using Wolfram language for many different purposes in server environments. Our goal has been to have a technology stack that's suitable for each of those uses, whether it's interactive notebook use, whether it's APIs behind a firewall where authentication is not relevant, but where clustering is relevant, whether it's different kinds of things. We want to make sure that we have a ready-made solution for all of those kinds of cases of deployment. And I think at this point, we've kind of filled in all the pieces and we now have that. And so if you want to deploy Wolfram language on a server, just contact our team and we most likely now have a ready-made solution for that. Something that's coming soon actually is using our remote batch submit functionality to be able to sort of seamlessly spin up thousands of kernels on remote cloud services. In fact, in 14.2, there's been lots of streamlining of parallel computation. For myself, I happen to have a few hundred cores that I just are sitting around for me, and I've been frustrated that I can't sort of start all those cores in parallel. They have to be started one after another. Now in version 14.2, they all get to start in parallel, and that makes sort of the use of parallel computation more convenient. Okay, another big thing that has come in version 14.1 actually, and it's being extended here, is standalone deployment. So the Wolfram engine is just a dynamic library, is deployable as a dynamic library, and you can call it from a C program using the expression API, and you literally write a piece of C code and it calls the Wolfram engine, and you can link the Wolfram engine into your C program and deliver that as a single binary, relevant for people with desktop software companies that are making use of our tech. And what's also interesting there is that you can strip down the version of the library so that you're only using those parts of Wolfram language which your application actually needs. And so you can often strip down that extra binary that has all the things you need from Wolfram language in just a couple of hundred megabytes. So for example, one application of that for us is LSP server, thing that does syntax coloring for IDEs, and that's just a 170 megabyte package, which includes a Wolfram engine. So that's another major deployment option, is standalone deployment now with the runtime, the Wolfram language runtime as a dynamic library, adding only a few hundred megabytes, which is nothing in today's world, to an application. All right. Also in the software engineering direction, another thing to talk about is something that has long been requested. Let me see if I can pull it up here. Is diff for notebooks. Something that's relevant if you're using source code, source control system. This is a diff, and so this is now taking two notebooks, and this is showing just in this notebook, it's showing the diff of what was deleted, what was added between these two notebooks. And so now we could go ahead and we could say, for example, here, could say, show me this sort of alignment chart of from the one version to the other version, what was added and subtracted. Or show me a diff between these two files. That's a summary. We could show an alignment chart between those files. It wasn't terribly exciting. We could show all sorts of different things between these files here. That's a unified view. Sort of symbolic representation of diffs is the story. And in fact, there is a diff object that you get. If I just say make these two diffs, that's a diff object. That diff object can be displayed in a variety of ways. It can also be applied to another thing to make the same diff to that. And so diff, you can use diff as a sort of direct kind of end user thing, like here's the diff between the Spanish alphabet and the Polish alphabet, or here's a diff between two genomes, hopefully. Okay, it's got to load in those genomes. There's the diff between those genomes. Viewing it, we can view it in a variety of ways. I wonder what happens if we say, what happens if we do that? Oh, wow. Okay, that's cool. For example, we could show that's just another view of that diff between those genome sequences. We can also do three-way diffs. There's a three-way diff between Latin, Spanish, and Polish alphabets, shown that way. Side by side, we could show it different ways. I wonder what that looks like. Okay. All right. So that's something relevant for using Wolfram language with IDEs. It's also a useful piece of functionality in its own right. Okay, well, if you're using notebooks as your primary environment, as I am, for example, people have often said, oh, don't put percents in notebooks because when you put a percent there, when you rerun the notebook, it's not going to work anymore. And you should always name everything, and sometimes it's convenient to do that. But let me show you a new thing, which is cell-linked percents. We've called it percent modernization. So let's say I've typed range of 5. I say, what's the median of that? I get the result. That's all good. But now let's say that I change this to percent squared. Okay? Total goof up, because the percent is referring to the result I just got, which was 9. Whereas what I really wanted it to do was to refer to the cell that was above, that had range of 5 in it. So let's do this again. Let's say range of 5, and now let's say median of, and I'm going to type a percent. And what I see here is this autocomplete that shows me these different cells which correspond to different lines. So let's say I pick that one. Now what I'll see is this linked cell, this cell-linked percent. And when I hover over it, I'll see it lights up there. And now I can say median of that, and I get 3. Okay, now I can go in here and I can put in squared, and it'll correctly refer to the that same input. So this is now a cell-linked percent rather than a kernel evaluation order linked percent. So this is and the UX of this is complicated, and we think we've done a good job in getting it right. There's sort of questions about what happens if you now quit the kernel, but yet you still have these things in the notebook. What happens if you're referring between different notebooks and so on? And you'll see all sorts of different iconography, which hopefully is fairly obvious. And sometimes it'll say, would you like me to reconstruct what that output might have been based on what I can see in the notebook and so on? And it will usually be able to do that. So a convenient way of doing interactive work with notebooks. By the way, when you go and you create a percent here, you'll have the option with this ... will immediately produce an iconized version. So the iconized version stores right in the notebook this form. And by the way, you'll see in a lot of different kinds of functionality, the capabilities to store locally, or for example, things like videos and so on. You can store them in the cloud, you can store them locally. It's important to know that you can store them in the cloud, because if you're going to send a notebook that contains a video to somebody else, and the notebook doesn't explicitly contain the video, but the video is just in your file system, the person who gets the notebook is not going to be able to deal with it. But what we now have is an option where you can save that video to a publicly to the cloud. So then the person who gets that notebook will be able to go to the same cloud object, retrieve that video, and use it in the notebook. All let's talk about LLMs. Well, one of the things that we added, so the ability to, okay, this is, okay, it knew my name. How did it know my name? It knew my name because of this LLM prompt generator that is as part of the LLM evaluator, part of the whole sort of apparatus that's being used to set up the LLM that you're going to use. So if I ask it, let's try this. Let's say, what is the street address of Wolfram Research's HQ? And for that, it's probably going to have to search the web. So what it's doing is it's using an LLM prompt generator that is using a web search, and then it's getting back the result, and the LLM is interpreting that result and giving us a narrative answer. Well, we can generalize this idea, and an important generalization is to use vector databases. So this thing here is a semantic index of my writings website with 11,000 entries in it. And so then I can ask a question. I can ask this question: when did I first see an eclipse? And it's going to use as a prompt generator that's based on the semantic index. And so now it's going to go to that, and it's going to, okay. So it answered that based on sort of the personal information of this collection of text that it had made a semantic index out of. It used that semantic index to generate a prompt, dynamically generate a prompt for the LLM, which then paraphrased the result and so on. So something that was new in 14.1 is the ability to create a semantic search index. And this is a vector database. And here what we're doing is we're creating something which matches definitions of words with words. It's going to take a little while to make this semantic search index. Doing that, it's making an efficient vector database where every word has been turned into this embedding vector that is, and then the role of the searching is to see, given the embedding vectors for these word definitions, given something that you're now talking about, compute the embedding vector of the thing you're now talking about. And the role of the vector database is to find the closest vector in what has been stored to the vector that you're now asking about. And I don't know how long this is going to take. This is the thing you get to do only once, but I don't know how long this is taking. Well, it'd be nice if it actually worked. What I was going to do here was surprised it's taking quite this long. I'm a little bit disappointed by that. But what I was going to show you was, given this semantic search index created from all the words in the dictionary and their definitions, that's 50,000 words or whatever. Oh, there we go. Sorry, 40,000 words. So now we can say a very large sea mammal. And now what it will do is it will find in the semantic search, it will find the embedding vector for a very large sea mammal, and it will see which word definitions were closest to that, had embedding vectors that were closest to that. And so in a sense, were closest in meaning. So we can make just a list plot of that, and we can see that whale has the lowest has the lowest distance, so it's the closest word to this meaning of a very large sea mammal. Okay, well, we can actually use create vector databases for anything. So for example, here I've got a bunch of graphs, and now I can directly use vector database search on those graphs to find, this is a new graph. This finds which of those existing graphs is closest according to this method of doing embedding to the graph that we already had. So we can use this for all sorts of different purposes, for text summarization, for all sorts of things. Well, so the general technology is a retrieval augmented generation. That's kind of the idea of using things like vector databases to do retrieval, to augment the generation of, for example, text by an LLM. And a thing to understand a little bit is sort of what can LLMs do versus what does computational language do? And the uh, um, the thing that uh, uh, I talked about this quite a lot in recent times. There's kind of LLMs kind of do things that are a bit like what humans do. They kind of think like humans. You can they you know, you can have them have sort of chains of thought that go a bit like humans and so on. They can do things that sort of unaided humans can do. They might be able to do it more efficiently and more and faster, but they're doing those kinds of things. The big other thing that we get to do is formalized stuff, the kind of stuff that we built over the last 300 years in mathematics and now in computation. That's something that LLMs are not very suited to doing by themselves. But if they call tools, like humans call tools, like Wolfram language, they can make use of this kind of computation capability as well as as well as their sort of thinking like capability. And just like there's retrieval augmented generation, a thing that we've been sort of the main source for is computation augmented generation. The ability to use computation to augment the kinds of things that LLMs do. You know, I think that the way I see LLMs as they're terrific kind of linguistic interfaces to many things, including computation. And that's where computation augmented generation comes in. I mean, the whole sort of AI industry is still a bit of turmoil, and I might talk a little bit later about kind of things I've figured out just recently about kind of the foundations of machine learning, which inform that a bit. But even as LLMs are sort of becoming quite generic, our direction of kind of making computational language, making a precise symbolic computational language remains and has been for decades completely unique. And we've been developing all sorts of tools for LLMs to use, all sorts of APIs and training sets and other kinds of things to help LLMs from the computation side. And it's you know, underneath the LLMs, we're using tools, mixtures of Wolfram language and Wolfram Alpha. Wolfram Alpha is convenient because it already has a natural language transport layer. It already talks the same language as the LLMs. And, you know, Wolfram Alpha has been sort of growing every week over the last 15 years, and lots of new capabilities get added. One that's quite recent is, let's see, is dark mode. There we go. That looks simple. It's actually really hard to do something like that, to get all the different characteristics of Wolfram Alpha to work well in dark mode. By the way, we've also added, we have Spanish language version, Japanese version, several more languages are coming soon. And by the way, talking of things like dark mode, something that's coming in version 14.2 is the notion of color vectors for notebooks in general, where you can kind of change the color theme, including dark mode for notebooks. Well, the LLMs do something else that's very important for us. They provide this kind of new level of interface to Wolfram language. And like, for example, I've been talking about all kinds of things here, and you might wonder, how am I ever going to find any of this stuff? Well, you can search the documentation, but sort of infinitely more powerful, you can ask an LLM that has RAG and CAG support, and then you can use what the LLM tells you to build kind of solid Wolfram language code that you can use. Now, to make use of LLMs, there are layers of practicality that need to be dealt with. So, for example, there are lots of LLMs in the world. We've been running a benchmarking project every week, actually. We put up this benchmark of Wolfram language writing by lots of different LLMs. You can see there are lots and lots of LLMs. All of those LLMs you can connect to from Wolfram language. We have service connections to all of those LLMs. And so what, and you can do things like I'm not going to run this because it's going to take too long to work, but you could run things like you can ask all sorts of different LLMs. That's the code to using different LLM evaluators to ask lots of different LLMs a particular question. Well, the something that's coming soon is our LLM kit and code assistant that is hiding the complexity of all these different LLMs behind a single kind of Wolfram LLM kit. And so what you'll see in the in settings now, you'll see, if I bring up settings here, you will see here under AI settings that you could pick a raw model, or you can pick just the Wolfram LLM kit and code assistant. This is on us, so to speak. So this is a separate subscription, and it will be coming soon. It's something that will be released independent of 14.2. It's a separate product that is our LLM kit and code assistant. All right, let's talk about the code assistant. This is an exciting and important thing that I think is really going to open up a lot of our technology to a lot more people. So, okay, let's say we go to the toolbar here, we press this button, we will get a sidebar here, which is a side chat where I could ask all kinds of things. Let's say, I don't know, let's say map of Roman Empire, and I can be very vague here, in 2nd century. And now let's just ask the LLM this, and it'll go, and I don't know what it's going to do, because LLMs are kind of wild animals. They do all sorts of crazy things, but hopefully it will respond in some way, and it'll be using a RAG and CAG mechanism underneath. Come on, wake up, LLM. Do something. That's not good. Let me see whether it comes back to life. This is what I get for running. Let me try. Let me just try running it again. Well, let's try this. That's not a good sign. All right, let me try starting this again. New chat. Let's try draw a cone. See if anything works. Okay, that's enough. So what I can do here is pull this over to my notebook over here and use that to draw a cone. And I could say something like, make it green. And that hopefully will do something here. I don't know why this is not working. Who knows? All right. That's not good. An unexpected error occurred. It's an error of the error. All right. Well, let me try and show you, just give you a sense of things that are possible here. So let me start up. Let's actually start a new notebook here. That might look better. Let's just go ahead and start typing. Let's just say that I type in, I don't know, a plot of an array function. It's plain text. Now I press this button here, and I press this light bulb, and the light bulb will go and say, okay, LLM, how would I fill in this notebook? So I've set a plot of an array function. Okay, it's decided that what I want to do is make that plot of the complex array function. Okay, now I could say, let me go to the top here and just make a section heading cell. And again, press this light bulb for inspiration, and let's see what it fills in. Okay, it says visualizing mathematical functions is one suggested title for that. Okay, let's go down here and let's say that I type in something like, let's say comparing Bessel and array functions, colon. And let me just put in a cell here let me press the inspiration button and let's see what it comes up with. And this is something you can do. Okay, well, what's it doing here? It's just showing, kind of weird. Okay, so it's actually writing those two things for my notebook. Both, for some reason, it's obsessed with complex plots right this moment. All right, and it's showing those two. I thought it might plot them on the same. Let's try asking it. Here, let's just bring this up. Make an ordinary plot of both functions together. Let's see what that does. Okay, there we go. Let's see what it's doing here. Now it's actually going to generate the plots, but I could equally well tell it to go and take this. Oh, here we go. It actually generated the plot for me. But I could also have told it to just use that in my notebook. And there it did that, and I can X this out. So it's rather impressive. Doesn't always work, but the point is you can see what it did. And if I didn't want a Bessel J, I might want a Bessel K here instead. I can change it. If I didn't want 1/2 here, I put a 2 here. The important thing is that it writes something that you can read. And that's sort of a unique capability made possible by the fact that Wolfram language is something that's intended to be read by people as well as written by people. Well, okay. So chat notebooks, which we introduced last year, are being merged into this whole code assistant mechanism. But the kind of the idea here is to the big idea of Wolfram language is sort of represent everything computationally, provide kind of a notation for computational thinking, and sort of Wolfram language sort of provides a superpower once you can formulate your thinking computationally. Code Assistant helps you crispen up your thinking to get it into computational form. Wolfram language is what makes it work. It's what provides the framework, the ability to execute things, the language that it can think in and humans can think in as well. So it's people here know what sort of this superpower of computational thinking in Wolfram language are all about, but relative to the number of people who could be using the technology that we have, it's still far too few. And I think Code Assistant helps to open that up. I have to say that you know, of the people who do get kind of this sort of superpower of computational thinking using Wolfram language, that's something that's unbelievably overrepresented among intellectual leaders. It's kind of always interesting for me as I work in new fields to find out, you know, the top person in that field happens to have been using Wolfram language for a quarter of a century. And it's kind of a repeated experience that I have. It's also very common among tech CEOs and CTOs that they themselves, with their own fingers, so to speak, will be using Wolfram language every day. And it's given that, it's sort of frustrating to see all those kind of programmers who are still using ordinary programming languages. And it's interesting to ask, why is that happening? It's kind of weird. People will tell me, you know, oh, I run some group somewhere and et cetera. And, you know, I just wrote this thing in Wolfram language and I could do in a couple of hours what took months for other people to do. And so why aren't the other people just doing things with Wolfram language? I think the reason is that sort of the job of a programmer is in ordinary languages is quite mechanical. A lot of that we've automated. If you're a CEO or CTO or a leader in some way, it's all about figuring out what to do. Kind of not a very perfect analogy, but a sort of an analogy. It's kind of an architect versus a bricklayer. If you're trying to build something, you need bricklayers, at least, and it's hard work, but it's not the same as being an architect. And it turns out, in the end, in the case of what we're doing with computational language, you don't actually need to lay the individual bricks because we've got this pre-assembled wall and it's Wolfram language. It's a function in Wolfram language, and you can just automate that part. So for people who are kind of leading things, it's all about figuring out what to do next. For people who are doing sort of ordinary programming language work, it's kind of that seems really hard. It's because what they're mostly doing is kind of straight line kind of writing pieces of code. And what we've spent the last 3.5 decades automating is a lot of that process. And what the place where you really need the humans is in figuring out sort of what to do next, taking that next kind of computational thinking step. And nowadays, AIs can do lots of low-level programming, but it's only really reliable if you can understand the pieces. And that's, again, where Wolfram language is really important. In any case, I think this whole code assistant technology stack will help many more people kind of get into computational thinking. It's it's kind of well, let's see, it's something which is, control equals has been a big success over the last 15 years of just generating like entities without like reading documentation. Similarly, with Code Assistant, you can produce snippets of code that you can build on. It really helps that we have hundreds of thousands of examples and we have a language that is sort of something that has words in it that LLMs can understand and learn from. And by the way, the LLM picks up pretty good habits from reading hundreds of thousands of examples. And so it tends to write pretty good code and puts it together. Well, okay, let's see. I think I'm running out of time here, so let me skip a few things here. But let me just say that sort of that this whole sort of paradigm of computation and computational language, as I've talked about a bunch in the past, it's kind of the big paradigm for our times and the thing that's kind of leading one to computational X for all X. And our goal is to provide the language, the notation for computational X for all X. And one of the things that has been something I've been interested in is kind of how do people learn the computational thinking that you need to do kind of computational X for all X? It's not traditional computer science, it's something different. And what is it that you have to learn? What's the computational X? What's the CX as opposed to CS that you have to learn? And people at these conferences have told me for years that I should kind of try and write something about that. And I finally started, although I have to say I haven't had as much time as I would like. You can find this on the web. The beginning of my effort at kind of a college textbook about introduction to computational thinking. It's been sort of an interesting exercise thinking about how to think about computational thinking, so to speak, and how to present it. We've been doing a huge amount in education, and we've got Wolfram U, which is producing lots of classes and delivering more and more courses. The new MOOCs this year: Introduction to Discrete Mathematics, Introduction to Finite Mathematics, Stochastic Processes, Electric Circuits, coming soon, Complex Analysis, etc. So we have an increasing fraction, for example, the standard math sequence as freely available online courses. We're now also producing even physical books. So we have a calculus book that just came out, and there are a bunch of other books in the making. Wolfram U has delivered a total of 718 hours of new content this year, 7,000 certifications issued. Other things that are going on, we have our academic innovation support team that's been doing workshops for lots of organizations about all sorts of useful and interesting topics. When it comes to in-person kinds of, some of that is in person, but another big thing that we have is our summer school, where we get to teach both content and methodology. And we have, you can see all the projects from the summer school are posted. You can see them, always interesting collection. We also have the Wolfram Winter School, which is more focused on our physics project and computational methodology around that. We also have the Wolfram Summer Research Program for, as the Winter School. We also have the Summer Research Program for, where did it go? For high school students. Where did it go? That's not it. Well, the Yeah, I think I didn't put that in here. Anyway, it's interesting to see the projects that high school students managed to do in 2 weeks with our technology stack. For me, it's always interesting because for the 3 weeks in a year, I get to be sort of do extreme professoring and invent 130 or so projects for that can be done with our technology. Um, I myself have, I should also mention our Emerging Leaders program, which is uh, kind of a year-round version for high school students and college students of our summer research program. Um, yeah. Um, well, I myself have also been doing all sorts of educational live streaming. Um, And I started at the beginning of the pandemic. I found it very educational for me, hopefully educational for people who listen as well. Many of these things have been turned into podcasts. And you can find, for example, well, I have 4 series, uh, Science and Technology Q&A for kids and others, Q&A about future of science and technology, Q&A about history of science and technology, and Q&A about business innovation and managing life. And I alternate between those things with 2 live streams typically per week. By the way, the other big thing, is that we've been for many years live streaming many of our internal design review meetings. For example, 14.2, you can, if you've watched those live streams, you can see our system. It's kind of an open design process. You can see the system being designed. And thank you to those who tuned in, and particularly thank you to those who made suggestions on those live streams. This year, I think I've done 170 hours of live streams, and you can find on the website. You can search for different kinds of things that we've discussed. So back from content, also in terms of ed tech, working with many schools and other organizations using our technology and APIs for kind of both for presenting courses and for assessment, all sorts of automated assessment technology. Also using our EdTech, our CBM project is getting increasing traction. And there's one other thing I want to show you. It's an ambitious project, which is using LLMs to make a tutor for Algebra 1, which is sort of a central course for many people. Let me see if I can pull this up. I should have a launcher for that. Oh, come on. It's gone. One second. This was a highlight, so I don't want to miss it. There we go. Okay, let's see if I can do this. All right. Graphic design is not adequate here, but let's register a new student. What should we say? We should call it John Doe. And I'll say start new session. So this is now using an LLM underneath. And what I'm going to do, start at the beginning. Let's see, how do I go through here? That's student registration. Name, John. Okay, it's just going to say, I'm going to use that. Oh, come on, tell me how old you are. I'm way too old to do that. Tell me questions about algebra. What is algebra? And why is it useful for basketball? Let's say. Okay, and it's going to write some essay about that. But more interesting is to go to table of contents here. Let's pick a section. Let's say, I don't know, this is kind of like an LLM created, LLM brokered course. So let's start with a point. Give me 2 and I will give you back 5. The plot will look like this. Give me another number. Okay, I'll give you 4. And now it should, and this is again, computation-assisted generation, and it's going to hopefully generate another plot here. Try another number, or think you know the rule. Oh my gosh, how am I supposed to figure this out? 2, 4, 5, 7. I don't know. Let's try x plus 2. Let's see what it says. Let's check your guess, which is the rule y equals x plus 2. Okay, here's a plot showing correct values in blue and values generated in light green. Okay. What about 3? I'll say. Great. When you give me 3, I'll give you back 6. Okay, so it's plotting that. Okay, well, how about I guess the rule? Maybe it's add 3. See what happens there. Okay, so it figured out that maybe it's add 3 meant that I was trying to say y equals x plus 3, and it says, okay, that worked well, good job. Okay, let's see. All right, let's go on to the next. Let's try doing this. Review question. Earlier question. Oh my gosh, 4x plus 2x. How am I supposed to know what that is? Well, let's say it's 8x squared. Let's check your answer. Start with 4x plus 2x. Let's combine the x's. Your answer was x. The correct answer is 6x. What do you want to do next? Well, let's say review adding 3x plus 5x. Don't overthink it. All right, I'm going to say 8. I'm just going to say 8. Really close. You got the number right, but remember to include the variable. Let's redo this problem. Okay, let's try saying 8x. And okay. So, you know, let's discuss this problem. I don't really like, I find algebra boring. I think I should write a program to do it instead. See what it says. Now, by the way, if we were watching, that's an interesting approach. Okay. If we were watching, I'm not sure if I can do this. If we were watching what's actually going on behind the scenes, we would see several different LLMs watching what's happening, and it would have said, "Oh, the student is going off track here," and it would have started. That's not a good answer. And it would have started trying to decide what to do, given that if you'd like to continue with algebra, try something else. Well, how about arithmetic? Okay, anyway, select a new topic, etc., etc., etc. The idea is that this is something that can be used autonomously to teach Algebra 1. So that's something that we're doing. And in general, what if you already have a course and you want to deliver it through LLMs? We have a thing we've been developing called Content Studio, which is a tool that we can use, and we expect to license it to service providers and so on to be able to take courses and make them kind of LLM enabled. Now, this Algebra 1 course, we're building as kind of an example of what you can do. It's much more sophisticated than what you can achieve directly, what you can sort of wrap around an existing course. It's something that's built from scratch as an AI-enabled course that we hope finally it will be possible for students to use autonomously. I mean, it has to be said that in the world of computer-based education, there are sort of 70 years of failures of people trying to build tools that can be used autonomously by students to learn things. And this we have, I think, between the technology stack that we're using, and the actual ideas associated with this particular project, I think we have the best shot people have had in a very, very long time. And it's sort of interesting to realize it's not just an LLM. You know, everybody can make the 5-minute LLM demo. What's hard is making something that can actually coherently work, and that's a lot of software engineering as well as kind of LLM prompting and so on. Well, okay, so we built lots of tools, some content. What really makes Wolfram Language and everything around it have success is the community that's developed, which includes you. A focal point for that community has been our Wolfram community. And we're seeing sort of more and more adjuncts on the community. We're seeing sort of more and more adjuncts to highly visible papers. Putting things on the community is great for sort of reproducibility of science. Community is also helping to promote work that people are doing. In the course of the last year, about 10,000 papers have explicitly mentioned using our technology. Many more have certainly used it. We've been starting to put out our sort of pick of the top 1,000 or so papers that we find, or the ones we find the most interesting, that have been produced using our technology. We encourage people to let us know about papers that use our technology and make sure to mention it so that they get picked up automatically. And I will say, talking of research, maybe I shouldn't go into this in much detail, but I originally built Wolfram Language, among other things, so I could use it myself. And I'm happy to say I get to do that almost every day. I've had a very productive time, particularly in the last 5 years. I think I've had the most productive 5 years of my life, actually. And that's sort of what's been made possible by the technology we have. And I think the metrics are fairly good. I've managed to produce 9 books, 4,000 published pages, lots of different things. In any case, the thing that has been building a lot of basic science to extend that process. One of the things that we've done in the past year is started Wolfram Institute, which is basic science operation that we're growing together with donors and grants and so on. 5 fellows so far, 15 affiliated researchers, 11 affiliated organizations, growing Discord server. And the goal is to take what we've learned from the company and apply that to the doing of basic science. Not like sort of academic institutions where kind of everybody is doing their own thing. It's something where we're trying to provide leadership to kind of leverage what we know and the ideas that we have about sort of how to move science forward. Well, I mentioned a few things that I've been up to. Let's see, I can just show you a few things. The sort of one of the things is all of the posts that I make. Every picture that you see in them, it has Wolfram Language code behind it. You click the picture, you get the code, you paste it into a notebook, you can reproduce the picture. It's kind of the way I think all publications should be done about science and so on, that it becomes sort of perfectly reproducible and extensible, and that's been an important thing. Now, the sort of a big story for me in the last few years has been our physics project, which continues to go really well. The thing I'm pushing for right now is sort of to understand experimental implications of the project, to kind of maybe we'll be lucky, like people were 100 years ago, in discovering that matter is discrete and that molecules were sort of big enough to sense with technology that existed then. Maybe we'll be lucky enough to find the discreteness of space with technology that we have right now, whether it's in astrophysics or in kind of quantum many-body systems or whatever else. I will say that the physics project has kind of led to a bunch of sort of new paradigms for thinking about things. I kind of see the methodology I'm using as being kind of anchored on the one side by sort of philosophy and on the other side by computer experiments. and it's kind of been a story of getting intuition from different kinds of projects. Well, okay, I've been recently had found out that the kind of paradigm we've developed gives us sort of new ways to think about things in biology, and new ways to think about actually also machine learning. And one of the things I was doing recently was to try to understand, kind of using Wolfram language as a crucial tool, and also ideas from our physics project and so on, trying to understand what's actually going on in machine learning. Why does machine learning work? And sort of peeling back the complexity of typical neural net machine learning to sort of see what's happening underneath. And I think I just summarized one thing that kind of figured out, which is sort of how does machine learning work? What is it? How should one think about it? It's kind of like if you want to build a wall, one way you can do it is to sort of engineer individual bricks and put them together in a very organized way. Another thing you can do is to build a stone wall and to just look around for rocks that happen to be lying around and try and find ones that fit in and try and build your wall that way. And in a sense, that's what machine learning is doing. It's looking for lumps of irreducible computation that in the training process, you kind of find that lump and fit it in, and that's how you kind of build up your capabilities. And so if, for example, you ask, well, how does that work? It's like asking, well, why is the stone wall built the particular way it's built? That's not something you're going to be able to answer. Well, in any case, that kind of this understanding of machine learning tells us a bunch of things about sort of where machine learning is going. It tells us about the importance of kind of computation as a different track from the sort of tradition of machine learning. It gives us some ideas about how one can mix those two things together. Well, it's I think it's sort of exciting to get this kind of computational paradigm to kind of relook at the foundations of everything. And that's something that has been kind of enabled both by Wolfram language as a tool and by Wolfram language as a way of thinking about things, kind of crispening up one's kind of computational thinking. It's sort of been exciting to see this kind of superpower of computational language develop. It's something that I think is quite historic in kind of the arc of intellectual history. There's still much further to go, though. For many people, as I said, what we have is still very much an artifact from the future. Those of us here get to use that future now, but many more people could. Frankly, we need your help to make that happen. I mean, we've kept our company small and agile. We're very pleased with the R&D and innovation that we've been able to do, but we have to rely on our community to kind of spread the word about what's possible. And I think we all want to see this happen. And I do want to thank everyone here who's been contributing to that, often over the course of very many years. So people might wonder, what can they do? It's certainly a good first step is produce great work by using computational language, Wolfram language, produce great content, do things in Wolfram community, make function repository entries, spread things around the web, on Wikipedia, wherever, sort of help to conceptualize what computational language can do in computational X for all X. And make sure you write good Wolfram language code, format it with elegant code, have it be something that really can serve as a notation for what you're thinking about, a computational notation for things. Where sort of when you write a computational essay or a paper, the computational language is carrying an important part of the message, not just for the computer, but for yourself and for other humans as well. I should say something about this conference. It's a very interesting group we have here. You'll meet all sorts of interesting people here. And I have to say, over the 36 years of doing these conferences, I know many collaborations and more have started at these conferences. So please don't forget to engage in networking, visit virtual booths, speak up, and so on. And we've also got a lot of people from our company here at the conference. Our company is, I think, a terrific team that we've assembled over the decades. And I encourage people to meet with folks from our company, learn who builds the tools you use, give them feedback. We appreciate any input you can give. And I think you'll find that you can have very interesting conversations with those folk and with each other. Well, I should just say thank you for being here, and let's go build the computational future together. Thanks very much, and I'll be back to do, after our Innovator Awards tomorrow, to do a Q&A. Thanks a lot. Bye for now.